Take it. All those in Zoomville who can't come to Zoomville, who are actually in virtual world, I guess, or onlinedness, I don't know what it would be. They too can participate in our lovely geometry stuff. All right. So we've been talking about triangles. So I have a couple of little questions for you to think about before we start going. And then we're going to kind of transition into quadrilaterals. That's the next big focus for us. And oh, I know what else I wanted to tell you before I really get going. If you have not yet gotten into Geogebra, okay, it's online software. It's free. Geogebra. Supposed to be a combination of geometry and algebra. You don't have to purchase it. Some devices, I'm not sure exactly how the student one works. You might have to download it, but I don't even think so. I think you can just do it online. You're just doing it online?
Like Desmos.
Yeah, like Desmos, okay. But you will need an account. So you have to create a student account, but they're free. So if you haven't done that, then go ahead and do that, because my plan is, if I can get the technology to cooperate, I haven't quite gotten it to help me yet, Tuesday of next week, that's week 4, I'll actually do some stuff with it in class on Tuesday so that you can see how it works and play with it a little bit and go ahead and hand out the first lab for Geogebra. So if you're here in Commerce, you can bring your device with you. Of course, if you're zooming in, you'll have your device. So go ahead and have your account hooked up to that device, ready to go, basically, so that we can talk about that on Tuesday. That's my plan. The technology works, okay? So get an account and all of that stuff. If you want to poke around in there first, then go ahead. And we will have our first assignment out of that. We'll talk about constructions a little bit, because we've already started playing with our compass a little bit, and what you can do in a construction and what you can't do in a construction. And then we'll see how much easier it is to let the software do those kinds of things for us than to play with the compass and the straight edge and all of that. So we'll work on that on Tuesday. All right, so before I forget, don't forget to do that. And if you're here, bring your devices, and then you can play on them and all that. Okay, so we were working problems on triangles. So I have a picture. It is basically a triangle inside of a triangle. And what it says is these two angles are congruent, and these two angles are congruent. These are 74 degrees. These are 72 degrees. Okay. Kind of a triangle that's nested, if you would, inside of the other triangle. And the question, and I actually really like these, hint, hint, hint. This actually came from a homework set, but the question is, what's wrong with this picture? And in your test, it might be, what's wrong with this picture? What's wrong with this statement? Correct this statement. You know, if it's a true false and it's wrong, you're going to have to say what's wrong with it and fix it. Okay, that kind of thing. So what's wrong with this picture?
Both triangles would have to add to 180. So
Okay.
because the tip, the top is going to be the same number twice. Either you're going to have to change 72 or change 74.
Okay. All right. So what I'm hearing is this triangle must add up to 180 degrees. Everybody agree? And this bigger triangle, the interior angles have to add up to 180 degrees. Now the problem is, the way I have these marked is basically they're both isosceles, right? So this piece is congruent to that piece, and I know that because these base angles are congruent, right? And then this angle and this angle mean these are congruent. Okay, they have to be so that the whole thing is isosceles. But what I heard was when you add this up, this angle for this triangle, did you figure out the actual angle? 36. Okay. But for the bigger triangle, it needs to be what? 180. No, the angle.
The top angle will be the same.
Well, it has to be because it's in the same picture. But when we do the math, this one I heard should be 36 degrees, but for the bigger triangle, I heard it's only 32 degrees. Okay. But it's the same angle. That's what Demondre said. Well, it's the same angle, so it's got to be the same measurement, right? So it can't be two different angles, two different measures. All of our math has to work. Just like the other day, whenever we had that one problem and we had like 5 ways to show something because we were using 5 different rules. The trick to that is every rule must work. Okay, if it's a rule, it's got to work, right? If it's one of those properties. So here, this has to be the same because this is one angle. Every angle is congruent to itself, right? It has to be. So what Ashley said was, I either need to change this 72, and I can make it what? 74, right? Okay. Or I need to change the 74, and then I can make it like 72. Okay, so those need to match is what she's telling me, because that's the only way both triangles will add up to 180. Yes.
I mean, you can only really change the bottom one, isn't that right? Because if you, 74 plus 74 plus 36.
Well, but if this one was 32, you'd be okay, right?
Okay, that makes sense.
Yeah, because I've got the 2 different measurements, so it's like, which one do we want? So yeah, I'm seeing Brian said, look, those are supposed to be basically corresponding angles, right? Okay, so this triangle to this triangle. Now these would be similar triangles, not congruent triangles, but it's the same kind of idea. If those are corresponding, then they should be similar, means all of your angles are the same, right? It's the lengths that would change on the sides.
And if a question like this was on the test, I guess, because like to me, the first thing that I thought about was the quadrilateral on the bottom adds up to 360.
Ooh, okay.
So I
Because you subtracted these from 180?
yes.
Yep. Okay. And then
That
what?
would be a way to prove it as well,
Absolutely.
or do you want just a triangle?
Yeah. So my thinking is this. My original thought is that upper angle, the tip of the triangle, so to speak, needs to be the same angle for both triangles, right? It can't change its measure. So my thought was the same as Ashley's, which was, okay, the 72 or the 74, one of them's wrong. Okay, so fix one of them. Okay, but if you don't see that and you say, oh, if I do this, then these angles are, I don't know what that number would be, but these angles are 108 each, and then 108 plus 108 plus, oh, that makes sense because it's 72, plus 74 plus 74 adds up to
364.
364, and we know it has to add up to 360 degrees. So my quadrilateral is also out, by the way, and that's what's going to happen when there's one thing wrong, like all your properties start messing up, right? Okay, none of them are working. And so if you find something else, a different property, and you just say, oh, that quadrilateral adds up to 364 instead of 360, boom, you're done. That's okay. And I'll go, I didn't think about that, and I'll make sure the measurements are right. Check. Good job. Absolutely. I tend to tell my students, whatever rabbit hole you go down, I'll follow you. Okay, so as long as your math is correct and your thinking is logical, like you're following a logical step, that's fine. And it really happens that way whenever we get to proofs in a week or two. I'll prove something one way and you'll go a totally different way, but you still get to the same answer. We're good.
Will we have instances where there won't be anything wrong, like it's a trick question?
No. If it says what's wrong, then there's something wrong. Unless I've just made a mistake, which happens, but probably not in that case. Everybody's good? Okay, here's another one. We're only going to do a couple of these and then we're moving on to quadrilaterals. I just want to make sure everybody is good with their triangle properties, because we are indeed moving on. So this is two triangles, but they're butted up against each other. They share this leg in common. It is A, F, E, and D. Does it really spell anything? Man, maybe it's deaf. D-E-F. Could be feed, but with an E-A instead of double E's. That's weird. Okay, I have a couple of congruent legs. The AD is congruent to the ED, and the AF is congruent to FE. Now what this says is triangle AFD is congruent to what? So it should be another triangle. And then why, or how do you know? Remember your naming convention. The corresponding parts need to line up when you name it. So if you're like me, you start thinking, what are my, well, these are congruent triangles. I have triangle congruencies. What are they? They're side, angle, side, an angle, angle, side, an angle, side, angle, and side, side, side. Well, I don't have any angles. And I don't see any of my special angles in there, like vertical angles that I could real quickly go, oh, those are congruent. So what do y'all think?
EFD.
EFD. So first of all, Demondre's giving me the naming convention, and he's doing it correctly. So the A to the F is congruent to the E to the F, right? So he named those in the correct order. And then the D was down there by itself, so I like that. So that's the correct triangle. And then on my message over here, Mary has told me side, side, side. Well, I don't see side, side, side. I only see side, side.
We share a side, so it has to be the same.
Okay, again, we haven't really talked about that property, but it's called like an identity, okay? That side has to be congruent to itself, okay? And you could say like same side or same segment, that kind of thing. So FD is the shared guy. So Summer says that guy has to be congruent to itself. And again, just make sure that you put it in the right order, like Demondre told me. So side, side, side. Everybody happy with that? And this one, I don't see any angles at all that could have helped me. So I don't think there's another. I think that's the only way you could do it. All right. One more of these triangle-y ones, and then we'll move on. Of course, we don't leave triangles along behind, right? They come along with us everywhere we go. So this one is similar to the bow tie guy that we had the other day. Kind of parallel lines like this. And then in between them, there are two transversals. Uh-oh. And those two transversals make two triangles. Boot up. So on the left, it's N at the top and I at the bottom, and T is the intersecting point in the middle. I guess that's nip. And then on the right, there's an A and an L. Could almost be nil. Tall. Nital. Latin. Oh. Latin. Sometimes I don't see it right off. They usually make words. I'm just saying, it's weird. Okay, so here we have this lovely picture, and all we know is that the two lines are parallel to each other, and here's what they have asked me. Triangle ALT is congruent to triangle what? And why? Alt, triangle alt.
I hate having to draw these out because I don't have two triangles that are congruent in my picture.
Well, that
But I
could
know
be
what it's saying.
beneficial. Who knows? Do we have anything congruent here? Okay, what we do have congruent is these two angles right here that are vertical to one another, right? Okay, because there's an intersection, and anytime you have an intersection of two lines, the angles that are opposite of each other are vertical. A lot of times I'll say, look, they make V's to each other, right? Okay, they share the vertex, and then there's a V coming out. So those guys are vertical, so that means they are congruent. Okay, so that guy and that guy. What else? On your test, they'll be drawn for you. That's my problem. Drawing a lot of tests. Yeah.
Are A and I congruent?
Angle A and angle I. Yes, angle. So you mean here?
Yeah.
If I kind of look like this on the inside right. And here's the parallel line with the transversal, right? So on the inside left. That's the part of A and I she means. I agree. Because those are all alternate interior because they're between the two parallel lines. Alternate interior.
L and N are congruent.
Okay, so can I use that same, let me turn my paper a little bit. These are the parallel lines. This is the transversal here. That same logic gives me this interior angle of L. It's a little difficult when you say angle L. If it's just on a triangle, it's easy. You can just say angle L. But here, angle L actually has 4, right? So be careful when you say that. But we know she's trying to get into this triangle, right? So this one that's on the left side of the transversal with N on the right side of the transversal. Everybody agree? Those are also alternate interior angles. Okay. All right. So right now we have what? Angle, 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 which is similar but not congruent. So we're getting somewhere because it didn't give me any congruency. So we've gotten somewhere. But now what do we need? We need a congruent what? Side or a congruent leg of one of those triangles. Does anybody see one? No. They didn't give me one, right? So unless there's something that tells me, for instance, if they said T is the midpoint of segment NL, if they gave me that little piece of information, oh yeah, we're all over that, right? Because then these are congruent, these two little pieces, right? Because midpoint means halfway. So if they had said something like T is the midpoint of AI, okay, then we could mark those two congruent. But they haven't given me anything like that. And so until they give me, I need one more little piece of information. They didn't give me anything like that. So what do y'all think? We don't know. So we can't fill that in. If it was, the problem here is, like, I don't even know at this point, like it could be ALT is congruent to NIT, because it could be that these are just flipped around this point, like folded over, reflection, okay? Or it could be that A lines up with the I because that's where they're congruent, right? That's the congruency that I marked. So it could be that this would be INT. And we just don't know. I mean, it could be that these are isosceles. So these two, oh, by the way, if T was the midpoint, they would be isosceles, right? Okay, because all of these would be congruent. So we just don't have that extra one little piece. So we don't know. Not applicable or don't know. Your book puts cannot be determined. That's what the book always puts, I think. Something like that. And so your y would be, I need a leg, right? I need one congruent leg, or one set of, I guess. Yeah, just one. We don't have to have all three of them, but we need one. Then we could tear it up. It'd be awesome. Okay. All right. So those are, again, just to remind you of some of that stuff we've been doing. Don't forget triangles as we move on to quadrilaterals, because they are not really going anywhere. They will haunt us the rest of the semester. In fact, one of the first things that we normally talk about with quadrilaterals is how many triangles we see. Okay, so that's not going anywhere, but it'll be back. We'll use those. And they'll feel like, oh, I just know so much about quadrilaterals now. Let me grab one. Everybody got one? Monty, did you get a quadrilateral?
No, ma'am.
Okay. Hopefully everybody at home has had a chance now to pull up that document. All right. So again, this is one of those definition-y things. I'm not going to spend tons and tons of time on definitions. So if you're not sure about stuff, go back and look. The nice thing about this particular page that I gave you, it's got this really cool diagram on it that shows you all the different things, and I'll get it closer to the camera in a second. But on the back side, it also has some properties. Okay, it also has some properties. So a polygon with 4 sides is a quadrilateral. So you can kind of look at, oh, those are the different properties. So if you're not sure, look at it. Okay, quadrilateral in general, just 4-sided polygon, right? Okay. And in fact, in your book, let me throw this out at you before we get too far. In your book, it talks about what is a polygon. Because I've kind of been throwing that word around a little bit, hoping that everybody knows what a polygon is, but just in case, what page do I need? Page 54. My book. So, the book, it says, look, these things are polygons, okay? Now, some of those look normal, the triangle and the quadrilateral, but then when they have this weird 1, 2, 3, 4, 5-sided guy, that's not what a pentagon looks like. It can be, right? Why don't we think it's not what we would normally see, right? Why? What's wrong with that pentagon? Normally, yeah, it's an abnormal one. It's actually what we would call concave, okay? And my geometry teacher in high school always said, it's like it's caving in on itself. You see that one of the vertices is on the inside of the polygon instead of on the outside. And so the diagonals don't all stay inside of the polygon is what's weird about it. So it is a concave one. Normally we deal with convex, which means that all of my diagonals go in between the vertices and it's all good, okay? But it is still a pentagon. Here's some example of not polygons, and I like this about your book, that's why I'm showing you. What's wrong with that ellipse? Why is it not a polygon? Doesn't have any sides or any vertexes, angles, right? Vertices. Okay, it's just one big, huge, circular, curvy thing, right? Okay, so curvy things, by kind of definition, are not polygons. Okay, why is, let's look at these weirdos. So that also explains why this one's not a polygon, right? Because it's got a curvy side to it too. But why isn't this one a polygon? Looks kind of like a polygon.
Is it because it's kind of like twisted?
Yes, it's because it's got these intersecting lines here. It looks like it might have at one time been a quadrilateral and they twisted the sides so that they would intersect. Or maybe it looks like two different triangles, right? So there's a few things. Let me throw one more. What's wrong with this? It's just a line, okay. And what's wrong with this one? Because that's a triangle. Okay, it's not completely closed. So there's some other words that start popping in, okay, that we kind of take for granted. Closed, okay. We know all of our polygons should be closed, right? They shouldn't, like we said the other day, it's not a triangle if the legs don't actually meet at a vertex, right? If it was left open on the side, it's not closed. So that's a piece of being a polygon. It's got to be a closed figure, okay? What about this one? That one was closed. What about this one? It's complex, okay? Because it's made up of two different triangles. This triangle is a polygon and that triangle is a polygon, but together they're not a polygon anymore, right? So it's not a simple figure, okay? So we need a simple, closed, three-sided or more object, okay? So 3 sides is the triangle. That's the smallest polygon I can possibly have. Because if I have 2 lines, will they close? No, it's an angle if I have 2 lines, right? Okay, if I have 1 line, that's not closed, it's just a line, okay? And they need to be straight lines, straight sides. So a multi-sided, simple, closed figure. That's what we're looking for polygons. So we're like, oh, polygons are easy, but they actually have a lot of little facets to them, right? A lot more than we might have thought they had. Okay. They've got a lot of vocabulary in this section. So what I'm actually going to do is I'm going to assign you guys to read it because I don't feel like I need to just go through every definition. They talk about vertices. I'll give you what pages it is in a little bit. They talk about vertices. They talk about sides of a polygon. They talk about what's consecutive. Consecutive means what? Next to each other, right? They're in order next to each other kind of thing. Diagonals. What's a diagonal? Here's my quadrilateral. I'll try to make it as close to what's on the picture there. It goes what? Let's name him A, B, C, D.
Lines between 2 non-consecutive.
Okay. A diagonal connects non-consecutive vertices, okay? So A to B is already connected because that is a side of the quadrilateral. So that can't be a diagonal. The diagonal has to go from, for instance, A to C. You guys see that? And by the way, in a quadrilateral, when I draw that particular diagonal, that actually splits this into 2 triangles. And we showed this the other day, right? The 180 plus the 180 gave me 360 degrees on the interior, okay? So we know that any quadrilateral I have, I can split it into 2 triangles, okay? So see, what about angle B? Does he have a diagonal? B to D? That's a diagonal. So if I didn't have the line from A to C there, the segment from A to C there, we would see these other 2 triangles, right? Okay, so the different diagonals cut it into different triangles. That's fine. What about C? Just the A that's already there, right? AC. So he's already connected to B, he's already connected to D. So whenever I have, for instance, quadrilaterals, and they are convex, not caved in on themselves, they should have 2 diagonals in them, okay? If it was caved in on itself, I can't even do that with a quadrilateral. I'll have to do it with a pentagon, like the one we had just a minute ago. Pentagon, just pent means 5, right? So 5-sided, okay? See, if this one is caved in on itself, let's call him E, F, G, H, I. and I want to do these diagonals. Well, from I, I'm good. I can do IF and IG. Both of those diagonals are inside, but from E, I'm in trouble. Why? I can't get to H on a diagonal without going outside of the Pentagon. See that? I can get to G, but I can't get to H unless I go outside of the Pentagon. And so that's the problem with the concave is, that's why we don't, it's not a problem, it's just why we don't normally deal with them, because a lot of times we want to work with diagonals on these polygons, and so we want them to be interior segments instead of having to go exterior. So that's what's up with that. Okay, so quadrilaterals. Which one would you like to talk about next? Landra, do you have a favorite? On you. No. Parallelograms, kites, or trapezoids? I don't care. I'm just gonna follow the little picture. Kites. Kites are the weirdo. I like that you picked them first. Let's talk about them. In this particular picture, you can tell why they get their name. They actually kind of look like a kite, right? Like an old-fashioned kite that you deal with. Oh, Samantha wants to do rhombus. Hold on to the rhombus, Samantha. I get there. Okay, so we'll go that path next. Okay, so kite. The reason why it's unusual and why it's all by itself is, let me give you a bit of a definition for trapezoid. Trapezoid has one set of parallel sides. Okay, let me put my picture back up. You can see them here, here, and here, right? Parallel sides. Parallelogram has two sets of parallel sides. You can see them. What do you think about the kite? He doesn't have parallel sides, right? His opposite sides here, this one's really long, this is an obtuse angle, this one's really short, and this is an acute angle. These two opposite sides are going to touch eventually, right? If we extend them out beyond the picture, they'll touch, okay? So they are not parallel, okay? So the kite doesn't have parallel sides. Okay, well, but why does it get its own thing? What do you think it does have? Look at it. Okay, so here's my kite. I'm up to I. Let's call him, see, I'm not near as interesting as the book is. I'm just gonna call him JKLM. JK, just kidding. No, I'm kidding. Kidding about kidding. Okay, sorry about that. Sometimes I get off on a weird path. So I heard that we think that it has congruent sides. Which congruent sides? Is JK congruent to KL? So JK is congruent to JM. And KL is congruent to ML. So everybody see that? I think it's pretty obvious in the picture, but that's actually the property. So a kite has two sets of congruent consecutive sides. Okay, so they have to be consecutive, meaning in order or not right next to each other, right? So this one is actually touching this one. They're congruent. Well, that's weird to us because, like, if we were in a rhombus, a rectangle, let's say, if we were doing a rectangle, the ones that would be congruent would be the opposite sides, right? The parallel ones. But here it's the ones that are actually touching each other. So that's kind of cool. Okay. He's the weirdo, but he's really neat and he's got a lot of cool properties. We'll get to a lot of them and see what's going on. But just so everybody knows what it looks like, there you go. There's a kite. Okay. So I'm not gonna go through every one of them. I'm gonna kind of follow Samantha's lead. She said, let's go down. She didn't really say it, but she said, let's go look at the parallelograms. Okay, because she wants to look at the rhombus. Okay, and here's the interesting thing as we start naming these things. We have to talk about what they are, and we have to talk about what they're not. Okay, sometimes. So, for instance, with a rhombus,